Good morning. Last session I talked about the role of chemistry of a steel grade, how does it affect quality. So, to understand that I have talked about the mode of solidification, the sequence of solidification which takes place when the particular steel grade comes during solidification comes from liquid to solid state. I have mentioned that the solidification sequence can be of two types, it is a delta or gamma or something in between. This is decided by the steel composition. Now, liquid may transform either to delta ferrite or to austenite gamma. So, the possible routes are liquid going through liquid plus delta to delta and finally gamma. Another route may be liquid going to liquid plus delta, then liquid plus delta plus gamma. That means, in the liquid state itself through peritectic gamma transformation is starting and then finally will become total solid austenite. Another sequence may be liquid going to liquid plus gamma, that means there is no delta, and finally going to solid gamma. It is important to remember that finally, irrespective of the chemistry, the solid solid type is austenite, whether we go through delta mode, delta plus gamma mode or gamma mode of solidification. Finally, we have austenite, but how liquid to austenite transformation takes place through different stages, that is what is important. So, there are three possible routes depending on the carbon equivalent for low alloy steels or plain carbon steels, and for stainless steels again the routes are similar, but the criteria there is nickel equivalent by chromium equivalent and not carbon equivalent. So, it is important to understand when delta transforms to gamma. Here you see particularly for these 2 and 3, delta rather in 2 delta liquid is becoming liquid plus delta ferrite, and then liquid plus delta ferrite is partly getting transferred to gamma through the peritectic reaction. Now, this is important, I have mentioned. It is important to understand when delta transforms to gamma during solidification. This route there is no delta to gamma transformation during solidification. Here also there is no delta transformation, only liquid going to liquid plus austenite and then finally austenite. So, delta to gamma transformation in the course of solidification, that means from liquid to delta and delta to gamma in liquid stage itself takes place only in the medium range of chemistry. So, there it is important to know when this delta is transformed into gamma, at what state of solidification this transformation is possible. This is very important. So, then I have mentioned that what stage of solidification, that means at what range of solid fraction Fs, this is very important. Because why this is important? Because the strength of solid shell is different from delta to gamma. So, the sequence of solidification is important to understand what is the strength of the solid shell, what is the ductility or the percentage area reduction of the solid shell during solidification. This is very important. Then basically I talked about from the iron carbon diagram high temperature portion, that when the carbon or carbon equivalent is less than 0.1, this is plain carbon iron carbon diagram for plain carbon steel. Here we have carbon content along the x axis, but if we have a low alloy steel where instead of carbon equivalent is important, which I have talked about, I will discuss today also what is the formula for carbon equivalent, how it is determined from the chemistry, that means from carbon, from silicon, manganese, other alloying elements, all this will finally chromium, this will finally determine what is the carbon equivalent in low alloy steels. So, if it is less than 0.1, the solidification takes place through delta only. If the carbon equivalent is between 0.1 to 0.5, this is the range, it is delta plus gamma. That means initially from liquid delta will form, and then there is a peritectic transformation, liquid plus delta giving rise to gamma. That means in the stage, in the sequence of solidification itself, delta will transform to gamma. Now the question is, depending on the chemistry, it is important to know at what stage this delta to gamma transformation is taking place, whether at the early stage of solidification or towards the final stage of solidification. That is very important. Now when the carbon equivalent is more than 0.5, solidification takes place liquid to liquid plus gamma and then to only gamma. So that means there is no delta during any course of solidification, any stage of solidification. So this is important, that how chemistry is playing a role in identifying what are the solid phases, what are the sequence of formation of delta or gamma during the course of solidification. And then I have talked about the modes, whether liquid to delta or liquid to delta plus gamma or liquid to gamma. There can be 3 possibilities. It depends on the carbon equivalent, and the relative amount of delta and gamma during and after solidification, this is also determined by the chemistry, that means carbon equivalent. And I have talked about the concept called Ferrite potential, which is given by this formula 2.5 into 0.5 minus carbon equivalent. For carbon and low alloy steels, the carbon equivalent can be found out empirically through this relationship. This has emerged after a lot of experimentation done by many metallurgists. So from the chemistry one can understand whether it will be delta solidification mode, delta plus gamma or gamma mode. When the carbon equivalent is less than 0.1, you see no gamma formation takes place, it is only liquid plus delta and delta 2. After solidification only delta to gamma takes place. So during solidification only liquid to delta. When carbon equivalent is between 0.1 to 0.5, so ferrite potential is between 0 to 1. For this ranges of chemistry, the solidification mode is delta plus gamma. That means initially delta is forming and then finally delta plus gamma is forming, and finally during solidification and finally only gamma, solid gamma is there. So if the chemistry or the carbon equivalent is more than 0.5, look at this, it's more than 0.5 means this becomes negative, ferrite potential is less than 0, then the solidification sequence or mode is only austenite, there is no delta formation. Then I talked about that in stainless steel this carbon equivalent is of no consequence. This cannot determine what is the mode of solidification. So there what is important is the ratio of chromium equivalent, ratio of nickel equivalent by chromium equivalent. Nickel equivalent is basically all alloying elements which are similar to nickel in making the stainless steel austenitic, that means austenite stabilizes these elements like nickel, manganese, carbon, nitrogen, copper, these stabilizes the gamma austenite phase. So we can find out nickel equivalent from this empirical relation, where all these manganese, carbon, nitrogen, copper are austenite stabilizers. So they are clubbed together along with nickel in determining the nickel equivalent. Similarly, chromium equivalent consists of chromium, which is a ferrite stabilizer, delta ferrite stabilizer, or moly, silicon, niobium, titanium. All these elements are ferrite stabilizers. So these have been clubbed together along with chromium, and finally chromium equivalent we can determine by this empirical formula. So if we know nickel equivalent by chromium equivalent, from this relationship we can determine what is the ferrite potential. Unlike for plain carbon and low alloy steels, their carbon equivalent is the criteria in determining the solidification mode. Here, since we have lot of chromium, lot of nickel, lot of other alloying elements, so carbon equivalent is of no consequence in stainless steel. Here the ratio of nickel equivalent by chromium equivalent is important. That determines what will be the solidification mode whether it is delta, delta plus gamma or gamma. So, the ranges are basically 0.55 to 0.74, these are the ranges. As you can see from this figure, if nickel equivalent by chromium equivalent is less than point, you look at here, it is 0.5, so this is around 0.55, around that, So, if it is less than 0.55, look at the transformation, liquid to liquid plus delta, then delta, and delta to gamma is basically a solid state transformation. So, during solidification there is no gamma. Now, when we go to a nickel equivalent by chromium equivalent of more than 0.74, this dotted line 0.74, from liquid it goes to liquid plus gamma, that means austenite, and then finally solid austenite. There is no delta ferrite for this range of chemistry greater than 0.74 nickel equivalent by chromium equivalent. When nickel equivalent by chromium equivalent ratio is between 0.55 and 0.74, then look at what is happening. Initially liquid comes to liquid plus delta ferrite, and then this temperature, these triangles, what does triangle? Delta to gamma transformation taking place at these points. So, as the nickel equivalent by chromium equivalent is increasing, the delta to austenite transformation is, the temperature is also increasing, and they are taking place at a relatively lower solid fraction. That means from delta austenite is becoming more and more stable. So, delta to gamma transformation is taking place relatively early in the solidification stage. So, if we look at the figure of say 304, stainless steel is a very common stainless steel. Here what is happening? Initially liquid, then liquid plus delta, and this delta to gamma transformation is taking place quite at advanced stage of solidification. That means when say delta to gamma, then the solid fraction is around say 0.5 or 0.9, then only this gamma transformation is starting. This has lot of implication on the toughness of the strand. So, this will come to discuss subsequently. So, what is important to understand is at what solid fraction delta to gamma is taking place, at what stage of solidification delta to gamma is taking place. Now, you look at the 301 stainless steel, where nickel equivalent chromium equivalent is less than 0.55, maybe it is 0.52, 0.53. So, here what is happening? Look at here, initially liquid, then liquid plus delta, and then solidification is complete, then also it is just delta. So, gamma has not started solidifying, has started forming during solidification. It has started forming only after solidification is complete. So, delta to gamma transformation is a solid state transformation here and not during solidification. So, 301 here again 430, these are equivalent as far as the solidification sequence is concerned, liquid to liquid plus delta, and then solidification is complete, there is no gamma. Here gamma since it is very low in nickel equivalent chromium equivalent, that means chromium equivalent is very high, nickel equivalent is low 430, the delta to gamma solid state transformation takes place at quite low temperatures, around maybe 1220 or 1230 here, and the solidification is complete at say 1420. So, for quite some time, so for about 200 degrees centigrade, only delta is present at solid phase, delta to gamma takes place only below this temperature. That means during cooling of the strand, at the time of continuous casting, after solidification we have only delta, and gamma is taking place at quite low temperature. That means delta will be, grains are available, dendrites are available and it is possible that there will be some grain growth, because when austenite forms at the grain boundaries of the delta, then only there is a inhibition of the grain growth in solid state. So, this is very important to understand at what stage delta to gamma is taking place, whether during solidification, if during solidification at what stage, like 304 at the final stage, almost at the final stage of the solidification. But if you look at 316, it takes place when the solid fraction is maybe say 0.3, 0.35, 0.4. So, it is quite early during solidification delta to gamma is transformation is taking place. 310S initially liquid plus gamma and then solid gamma. So, no trace of delta ferrite, as I have told you, beyond a ratio of nickel equivalent of chromium equivalent of 0.74, it is only gamma transformation during solidification, liquid to gamma only, no austenite. So, every grade, if we know the chemistry, we can find out what is their solidification sequence. So, this is very important. So, as I mentioned that depending on the chemistry, we can find out nickel equivalent by chromium equivalent, mode is high is the nickel equivalent relative to chromium equivalent. So, more will be the gamma solidification tendency, less is the nickel equivalent, it will be delta solidification mode, that means more ferritic solidification, and higher the nickel equivalent by chromium equivalent, more than 0.74, it will be austenitic solidification, gamma solidification. So, this is important to remember that chemistry plays a very important role in identifying the solidification sequence, whether it takes place through delta or delta plus gamma or gamma, that is austenite. So, this is very important to remember. Now, let me talk about the concept of segregation of alloying element. This in a very preliminary fashion I have discussed earlier that during solidification all alloying elements, steel is basically an alloy of iron and other elements, other alloying elements like carbon, there may be silicon, there may be manganese, there may be chromium, there may be nickel, phosphorus, sulfur, all sorts of alloying elements, that means solutes are there in the solution. So, it depends what are the alloying elements are there, but one thing is common, that during solidification the solid has less amount of these alloying elements. The liquid becomes slowly more rich and more rich in the solute elements. This is called segregation. Segregation means the solute alloying elements are segregating, that means they are preferentially moving from solid to liquid. They are segregating, they are preferentially going from solid to liquid. So, this is called segregation. There is a partition, there is a diffusion, there is a movement of alloying elements from liquid to solid, just the reverse, from solid to liquid. The liquid is more rich in the alloying elements, it becomes more and more rich. So, micro segregation during solidification that results in increase in concentration of an alloying element, except iron, all other alloying elements will undergo this segregation. So, all alloying elements from their origin, if the original value is C0 in liquid steel, suppose say we have taken a steel where the carbon concentration is say 0.1. Now, during solid, so the original value, that means C0 for any alloying element, say carbon for that, let us assume, is 0.1. So, initially the liquid has, after solidification, the liquid after it has become liquid, that means when you heat it up it becomes liquid. So, liquid steel, the concentration of the initial concentration C0 of that particular alloying element, say carbon, it can be silicon, manganese, phosphorus, anything, sulfur. So, that is C0. So, during solidification the value of carbon in the liquid increases and the value of carbon in solid decreases. So, the last solidifying liquid, if you denote it as Cl, it is much higher compared to C0, and this is can be found out from the modified Shale equation. Shale was the first who tried to find out how the concentration will increase during microsegregation during the course of solidification. So, and finally original Shale equation was modified and then by Cruz, and then it becomes a modified Shale equation. Here just look at what are the factors. C0 is the initial concentration of the alloying element, Cl is the concentration of that particular element in the last solidifying liquid Cl. So, if there is an increase from C0 to Cl, now Cl it has increased from C0, how it is related? It is related by the solid fraction Fs. Small k is the distribution coefficient of alloying element between solid and liquid. This k is a thermodynamic entity, it depends on the particular phase diagram, any phase, say iron carbon, if you look at plain iron and carbon, you can find out what is the value of K at different temperature. So, that is means the ratio of solubility of carbon in liquid in solid divided by liquid. That means K is always, since the solubility in solid is less than the solubility in liquid, so K is always less than 1. So, this K distribution coefficient of alloying element between solid and liquid is the ratio of concentration in solid divided by liquid is always less than 1 for all alloying elements. Now, this small a, this is a back diffusion parameter, that means whatever alloying element is there in the solid, so it will try to be the solid which is forming later on during solidification, it is relatively rich in the alloying element compared to the solid which has formed earlier, and moreover the liquid is also having more of that alloying element. So, there is a possibility of back diffusion in the solid. So, this is determined by this back diffusion parameter A is determined by the d as the diffusion coefficient in solid, Tf is the local solidification time, that means time taken for local solidification. So, it again depends on the temperature difference between the liquidus and solidus and the rate of solidification. TL is the liquidus, Ts is the solidus. That means the temperature difference between liquidus and solidus divided by the rate of cooling, the local rate of cooling at that particular particular distance, particular time of solidification. So, this gives the local solidification time, and L is the secondary dendrite arm spacing. This L is again proportional to the rate of cooling, because this secondary dendrite arm spacing gives the size or indicates the size of the solid dendrites. So, thicker as the dendrites are, the diffusion will take more time. So, it takes long time for diffusion to take place. So, that is why secondary dendrite arm spacing L is important, diffusivity ds is important, diffusion coefficient, the local solidification time is important, because mode is this difference, mode will be the solidification time. It of course depends on the rate of solidification. So, with all these factors it is possible to find out Cl with respect to C0. So, Cl is always more than C0, that means due to the small value of K, Cl becomes more and more rich in that particular solute. So, please try to understand the segregation of alloying elements will make the concentration of that particular element in the last liquid which is solidifying more rich compared to the original value, and because of this we call it segregation. So, the last liquid which is which will finally solidify, is relatively more rich in the solutes. This is true for all solutes: carbon, manganese, silicon, phosphorus, sulfur. Now, to what extent this segregation will take place depend on this value of k. I will come to it. More is the segregation means lower is the small k, because k is basically the ratio of solid by liquid, ratio of concentration in solid by liquid for a particular element. This is always less than 1. So, suppose small k is 0.1 for a particular element, that means the liquid is becoming more and more rich in that particular element compared to the original concentration. And take another element where k is say 0.8, so it is relatively less segregation, we will have less segregation of that particular element. So, lower is the value of k, more is the segregation, the liquid will become more rich in that particular element. So, the final solidus temperature will become more suppressed. So, the difference between liquidus and solidus become more wide. So, segregation has a lot of implications during solidification. What are the implications? As I have told you, lower the value of k, more is the segregation. So, those elements whose small k, that means the segregation ratio or the distribution coefficient is quite low, those elements will create more segregation. More segregation means the concentration is of the final liquid which is solidifying is quite rich, much more rich compared to the original value. So, what is going to happen? More amount of segregation, and because of the segregation the solidus temperature is getting more and more low. So, the temperature interval for solidification, temperature interval between liquidus and solidus, the solidus is becoming more and more low as k is low. More low is k, Ts will become more low. This I will discuss in details subsequently. So, you will come to know what are the implications of segregation. So, please try to remember segregation is a factor for all allying elements. It is a question of whether it is relatively more or less. Now, another important thing is segregation is not equal when solidification is taking place between delta and gamma or gamma. If it is through delta, segregation amount of segregation is something. If the solidification mode is through gamma, for that particular element, allying element, the k value, that means the extent of segregation may be different. So, we have to know what is the k value for delta segregation, delta solidification, what is the k value of that particular element, allying element for gamma solidification. So, lower is the k value, more is the problem of segregation, more is the suppression of liquidus temperature. So, we have to keep in mind what are the implications of these. So, this will be becoming more and more clear as I go ahead with this concept.